Okay, so, well, first, thanks to the organizers for inviting me to speak at this. It's nice to be at a workshop with a beach again. It's been too long. So I was asked to give an introduction to T and U-duality invariant formalisms, which I've interpreted as meaning I should give an introduction to the ideas surrounding double and exceptional field theory, in which case this title is not 100% accurate. I wouldn't say these formalisms are exactly invariant under T or U-duality. They're certainly inspired by and constrained by duality symmetries. So hopefully that will become clear as I explain the talk. And I should mention this is all based on a review I wrote last summer with David Berman. So please see that review for firstly all the technical details I will omit during the talk, but also for all of the original references. I've decided to give a clean presentation without any original references cluttering up my slides. So I'm going to start by giving some context for sort of the bigger picture and the motivation for these formulations. So I'm interested in understanding, let's say, the geometry and symmetries of string theory and M theory. And frequently I will just look at their low energy limits, which is given by supergravity in 11 or 10 dimensions, where you just see the massless modes of these theories, which always include the metric, and then some p-form gatefields, and then some fermions, which will not appear anywhere else in this talk. And everything that I'm going to say really flows from the fact that in these theories, there are very many interesting dualities, meaning equivalences between different versions of string theory, or equivalences between the same string theory, but in very different geometries or in different strong or weak coupling regimes. So maybe the most familiar of the dualities that I'm interested in is T-duality, which you may have heard of in textbooks or in courses on string theory. So the simplest statement is that if I put a string on a circle of radius r, it's equivalent to a string on a circle of radius 1 over r, as long as I swap the momentum of the string in the circular direction with the winding of the string around the circle. And if I put strings on a d-dimensional torus, I can do more transformations involving more momentum or winding modes. If I extend not from T-duality, but all the way to U-duality, then I also have transformations that exchange momentum modes of the string with winding modes of branes like D-branes or the NS5 brane, while also doing something interesting to the geometry of the background that the string is in. So T-duality, I should say, is tied to string theory. This U-duality is present in string theory, but it's also somehow non-perturbative and is meant to be a duality symmetry that occurs in M theory in 11 dimensions, where you don't have strings, but you do have other branes like M2 branes, which will get exchanged with M5 branes. So all these dualities really come from the fact that strings and branes are extended objects. So they have this capacity to wind around compact directions. And then that leads, in some sense, to these dualities, which are present everywhere in these theories. Now, in the supergravity limit, this is a low energy limit. It can also be thought of as a point particle limit. So it forgets, in principle, about the extended nature of the theories, of the objects in the theories that it comes from. But despite that, the classical version of these duality symmetries is still present in the supergravity theory. It shows up, though, however, in an interesting, non-obvious way. So if I take my supergravity and if I do a Kaluza-Klein reduction on a d-dimensional torus, I find in the reduced theory, the lower dimensional theory, after the reduction, that there is an enhanced global symmetry associated to the presence of the T or U duality symmetry in the full theory. So for instance, if I reduce 10D supergravity on a d-dimensional torus, I get an enhanced ODD symmetry, which is the T duality symmetry. And if I reduce the 11D supergravity on a d-dimensional torus, I get a more interesting symmetry associated to the exceptional Lie groups, which I denote by E subscript T. And okay, this is an unexpected global symmetry that appears in the reduced theory. From the 11 or 10 dimensional point of view, it's a sort of a hidden symmetry. You wouldn't naturally realize it was there. If you start with 11D supergravity, you have a metric and a free-form Gates field. There's no trace of something like an E8 structure, but it emerges when you dimensionally reduce. And then also these dualities are very much non-geometric in the sense that they mix metric and form degrees of freedom. So they don't respect that originally there was some well-defined geometry with a metric and fields living in the geometry. After doing a duality, things get mixed up in a way that you can trace all the way back to the fact that you're exchanging momenta and winding. So one of the questions that double and exceptional field theory were introduced to answer was the question of whether you can reformulate supergravity in some way so that you would always be able to see the presence of these ODD or ED symmetries at the level of the full 11 or 10 dimensional theory. So this is exactly what these theories managed to achieve, and they do this in an interesting way. So practically speaking, DFT or XFT provide a way to unify and reorganize all of the different supergravity limits of string theory and M theory. They promote these ODD or EDD symmetries that appear after dimensional reduction. These get promoted, in fact, to local symmetries appearing in some generalized notion of diffumorphism, which we will review in this talk. And then it works with a new idea of what the geometry of the theory should be. Instead of working with the metric and form field degrees of freedom separately, it already organizes components of these fields into representations of these groups, ODD or ED. And it does this in a way that allows you to say that an ODD or EDD structure or symmetry is manifest in any background before doing a compactification. So I wouldn't quite say this is exactly the symmetry. It's more that there's an ODD or ED structure controlling what the theory should look like. If we would really want to describe this sort of generalized geometry in a way that's fully invariant under duality symmetries, what we might actually want would be to have some extra input from up here, from the full string and M theory. So I've aspirationally positioned my label for DFT and XFT sort of halfway between supergravity and the full string and M theory. The idea is we want ingredients in our reformulation which remember a little bit more about the fact that these were theories of extended objects which could wind, and this was important in the origin of these symmetries. So what we do in formulating DFT or XFT is we introduce an extra stringy or brainy ingredient in the form of extra coordinates. So the underlying logic is fairly simple in that the usual space-time coordinates should be conjugate to momentum modes of the string, let's say. And under duality transformations, you mix up momentum modes with winding of the string or of other branes. So if you put momenta and winding on the same footing, it motivates introducing extra dual coordinates, which here I denote as x tilde, which should be conjugate in some sense to winding. And then you really want your duality symmetries to act on x and x tilde together and to build some sort of doubled or extended geometry which sees both the original space with coordinates x and in some sense the dual space with coordinates x tilde. And I should say that these dual coordinates are really there. You see them when you're doing duality on the world sheet or also in string field theory. So what we can do is formulate the theory of DFT or XFT as if we have these extra coordinates, which should be associated to the real genuine duality symmetry. That would give us something that looks like it's formally completely ODD or ED invariant. However, what we'll find in a few slides is that there's a constraint which tells us you can't actually have all of these coordinates on the same footing. You have to select some subsets, some D of them, the x's, say, not the x tildes, to be the actual coordinates of your space-time. And when you solve that constraint, you can still use this formulation. It's now then really a version of generalized geometry written in different notation, but it will break the formal ODD or ED that you've used to formulate the theory. Despite that, it's still useful, and there are situations in which you do see these coordinates playing a role. So the idea is that the full string theory, certainly on toroidal background, should see a geometry with these extra coordinates. And by formulating supergravity in this doubled or exceptional way, we take a step towards understanding this sort of more fundamentally stringy or brainy picture. So that's my basic high concept overview. I'll pause in case there are any questions. I can't see the chat. So I assume if there are any questions, somebody will read them out to me.
Not yet. Okay.
So having said all this, trying to set the scene and trying to argue that I'm interested in studying these big symmetry structures and string theory and M theory and whatnot, I'm now actually going to try and explain the theory of D of t and X of t by sort of ignoring, to some extent, this story about dualities. I'm going to try and build it up using a different perspective, which is to view it as a generalization of Kaluza-Klein theory. Because there are many sort of nice conceptual similarities between what we do in D of t and X of t and in Kaluza-Klein theory. So I don't know how familiar everyone in the audience is with Kaluza-Klein, but perhaps the vague idea is I think, quite familiar because it's a very famous idea in the history of physics from 1 century ago. And Kaluza-Klein theory originally was this attempt to unify gravity and electromagnetism by viewing them as descending from a purely gravitational theory in 1 dimension higher. This was maybe the first place that extra dimensions played a role in physics. So one way to phrase this is to say if I have a d-dimensional theory with a metric and a one-form Gatefields, I can view these as coming as components of a metric of some d plus 1 dimensional theory. And the fundamentally useful perspective on this is to look at the symmetries of the d-dimensional theory. So both the metric and the one-form transform under diffumorphisms, which infinitesimally are generated by some vector v via the Lie derivative, which I denote by LV. And this one form also has the usual U1 gauge symmetry where it changes by d of a scalar. And I can put my vectors of diffumorphisms together with the scalar to form a d plus 1 dimensional vector. And it turns out that the d plus 1 dimensional diffumorphisms acting on this d plus 1 dimensional metric reproduce exactly the symmetries of the d-dimensional theory if I assume that I truncate to the situation where none of the fields depend on this extra coordinate, which I've denoted xt plus 1. Importantly, I can't just get a metric and a one form out of a metric. I also have to have this extra field, which is some scalar, which you can think of geometrically as corresponding to the radius squared of the extra dimensions. But then, okay, what you say is once I have this higher dimensional theory, I look at its action, which is obviously just Einstein-Hilbert. If I assume this Kaluza-Klein truncation to the, let's say, the 0 mode sector, I can reduce this action and I get Einstein-Hilbert in the lower dimensional theory. I get field strength squared for the Gates field, and I get some kinetic term involved in this case. So this is an old idea that's sort of reused and reused constantly in supergravity and string theory. So now we want to generalize it in a new way. So Kaluza-Klein theory gives a nice geometric perspective on the symmetries of a one-form theory coupled to gravity. So a natural question is, well, what happens if I have a two-form B instead of my one-form A? The reason I would take this step is because while one forms couple naturally to particles, two forms couple naturally to strings. So every string theory has, as a massless mode, a two-form Gates field of this form. So now in our d-dimensional theory with a metric and this two form, we again have a diffeomorphism symmetry, but now the gauge symmetry of the two form consists of one form Gates transformations. So we might just ask, well, can we play the same game? Can we put our vectors together with these one form gauge symmetry parameters to get some 2D dimensional vector? Can I introduce d extra coordinates, which I will write as x tilde with a lower index, because I'm sort of copying the structure of the one-form Gates transformations? And can I hide this g and b in a higher dimensional metric in a way that reproduces the symmetries if I do some sort of Kaluza-Klein style truncation? And you can check by trial and error that this basically doesn't work if you just use the ordinary notion of a 2D dimensional diffumorphisms generated by the 2D dimensional Lie derivative. However, what does work is a more intricate and more interesting structure which uses some hidden symmetry. The hidden symmetry turns out to be an ODD structure. So the point is, when I have these doubled, or I will now call this a generalized vector consisting of a vector and a one form, there's a natural way to pair the vector part with the one form part given by the obvious contraction. So if I have two generalized vectors, I can write down a bilinear form involving this quantity eta, which is some bilinear form which is preserved by ODD transformations. So it has this off-diagonal form. If you diagonalize it, you have plus 1d times and minus 1d times on the diagonal. So it's a split signature orthogonal form. And it turns out what will work for us is if we take this ODD structure to be fundamental and require the perhaps radical step that we'll change our notion of what a diffumorphism is. We'll change our notion of the local symmetry and say that I'm going to define a generalized Lie derivative, which I denote by calligraphic error, which has to preserve this ODD structure. It has to preserve the pairing between vectors and forms. So how does this work in practice? This leads to a notion of what I call up here generalized diffumorphisms. So now if I take two generalized vectors, which I should think of as a pair of a vector and a one form, I can write down the following derivative, which is a generalized Lie derivative of u acting on v. So these first two terms are the usual Lie derivative. And then there's this extra modification in which this ODD structure appears explicitly. And here I'm writing derivatives with respect to these, the original d coordinates and these extra d coordinates that I'm sort of trying to introduce into it. Now this is not quite like the ordinary Lie derivative, which you can easily see here is antisymmetric. Adding this extra term means this is no longer antisymmetric. It's not really a problem. What we would really like to keep is the fact that we have some closed algebra of symmetries. So for the ordinary Lie derivative, if I take the commutator of two Lie derivatives, I get the Lie derivative of the commutator under the Lie bracket. So I can require the same condition here, which will ensure I have a consistent symmetry algebra, using here as my generalized Lie bracket, the anti-symmetrization of this. And then I can go and calculate this to see if it's true. And I find there are obstructions. And the reason there are obstructions is because I've actually introduced these d extra coordinates. And what you find is that, well, you end up with a bunch of extra terms on the right-hand side that you don't want. They all involve these partial derivatives contracted with this ODD structure. So remembering that this pairs vector and covector indices, all of these obstructions look like the usual partial derivative hitting some stuff times its contraction with these dual partial derivatives with the new coordinates hitting some other stuff. So a pretty drastic way to make this work is to impose as a constraint something called the section condition, which is whenever I have a pair of derivatives contracted in this way, hitting either fields or products of fields, it has to vanish. The way to solve that is to say that actually these extra coordinates that you tried to introduce, no fields can depend on them. This is a stronger constraint than what you have in Kaluza-Klein theory, where you do a truncation to the zero mode sector. And you could still have this massive tower of fields if you think about doing this, let's say, Fourier expansion of the dependence of the fields and the extra coordinates. Here, that entire tower is killed at the start by this condition. It's really saying you cannot depend on these extra coordinates we've introduced. The crucial thing, though, is that the constraint we found is entirely, well, the constraint is agnostic about whether you choose the x tilde or the x as the coordinates that you don't depend on. So there's some freedom to work with the theory and then make the choice about which coordinates are physical at the very end. So that's the philosophy that we'll now continue with. So before I explain a little bit more about the theory, I can make some connections to tomorrow's talks. So you might ask, well, let me impose this constraint. What actually is this generalized Lie derivative? So it involves pairs of vectors and one forms. And if you actually work out how it acts, you find that it just involves things like the ordinary Lie derivative of the vector parts, and then Lie derivatives and exterior derivatives acting on the one form parts. So this is the notation that would be used in generalized geometry. It's a somewhat more poetic notation, so you can learn, you will see more of that in the talk tomorrow by Tennyson. Another point which is interesting and is really kind of crucial to how this notion of a diffeomorphism is very different to the usual one, is that there are vectors, generalized vectors, which don't generate any transformation. Acting on anything, they just automatically give zero. And this corresponds to cases where this one form is itself closed. That is kind of coming from the fact that your B field had these one form Gates parameters. If the Gates parameters are themselves closed, they won't generate any change of the B field. So you have sort of Gates transformations for Gates transformations. There's a reducibility present. This reducibility is also kind of useful because, for instance, this generalized Lie bracket doesn't obey the Jacobi identity. But the failure of the Jacobi identity is just a transformation of this type that will be trivial acting in any fields, so it doesn't cause any problems. And this sort of reducibility is, I think, going to be the sort of crucial starting point for what Alex will be talking about tomorrow. Okay, so that's the basics of this new formulation of the local symmetries. I described it for vectors. You can now go and do all the things you normally like to do in geometry, keeping in mind this constraint. For instance, you can extend this to tensors using the Leibniz rule. This is how it acts on a symmetric rank 2 tensor. Obviously, we like symmetric rank 2 tensors because they allow us to define something that looks like a generalized metric. And so actually, in double field theory, we take our metric to be symmetric. We also take it to obey a compatibility condition with the ODD structure, which says that generalized metric itself defines an element of ODD. Slightly more technical terms, it's an element of a coset ODD over some double copy of OD. And this is a bit like a generalized Lorentz group. An ordinary metric would be in GLD over OD, let's say. The reason I do require these constraints is purely so that the generalized metric has the right number of degrees of freedom to exactly describe a metric and a B field. And when you do the solution of the section condition and you work out how the components of this tensor should transform, you find that it can be parameterized in terms of a metric and a B field in the following way. It's quite nonlinear, but it reminds you a little bit of what the Kluse-Klein ansatz look like for a metric and a one form. Except that it's got metric and the entire inverse metric are contained in this object. So this is our basic physical field, except for one small technical complication, which is now we want to describe the dynamics. So this is something I think you can think of as being like the Kluse-Klein scalar, which had to appear in the Kluse-Klein story for the whole thing to be consistent, but also just because the degrees of freedom of the higher dimensional metric called for it. Here, the issue is slightly more subtle. That generalized metric that I showed you turns out to have determinant 1, which means I can't use it to write down a measure for integration. I want to write down the square root of det h or something like that, but that's trivial. So I do something a bit odd. I introduce something I call a generalized dilaton. It's a scalar field. I define its exponential to have this weight 1 transformation, which means I can write e to the minus 2d as some scalar field, which is I will call the actual dilaton, times something of weight 1, which has to be identified with the square root of the determinant of that space-time metric. Okay, it's some extra fields that makes things work. It allows me to write down an action, which is invariant under generalized diffeomorphisms. So how do I find this action? In Kluse-Klein, it was obvious that we had to use the Einstein-Hilbert action for the higher dimensional theory. Here, because we've based everything around generalized diffeomorphisms, the usual notions of connections and curvature are not the right ones. They won't transform correctly. You can define generalized connections, generalized curvatures. It's just a bit more work. But you can also do something by brute force that you could also have done for the Einstein-Hilbert action. So here what you do is you just write down everything that is second order in derivatives of the generalized metric and this generalized dilaton. You write it down with unknown coefficients, you vary it under generalized diffumorphisms, and you require that what you have at the end of the day is a scalar. And up to terms it's vanished by the section condition. There's a unique result, which I've written in this box here. You can think of this as a generalized Ricci scalar. And then you can write down an action where technically I only really want to be thinking about integration over half the coordinates. So I'm always solving the section condition. When I do solve the section condition for this action, this somewhat messy expression involving metric-like quantities magically spits out a following action, where you'll see I get Ricci tensor for the metric, I get a field strength squared for the B field, and then I get some kinetic terms for the dilaton. And this action might be familiar to you. It is, if I set d equals 10, it is the NS sector of type 2 supergravity. If I set d equals 26, it's the low energy effective action of the bosonic string. So it's this sort of universal piece of the low energy action of strings. So the thing that's interesting or unusual here is that I started off by talking about T-duality. So if I would compactify this action on a d-dimensional torus, capital D-dimensional torus, I would find a lower dimensional theory with an ODD T-duality symmetry. So for instance, the metric and the B field and the torus would combine into a generalized metric given by the same expression that I wrote down on the last slide. And that would transform under ODD T-duality transformations as a rank 2 tensor. Here, on the other hand, I've reproduced this action by starting with something based on ODD in d equals 10 directly, without making reference to dualities or tori, just postulating that I should have a generalized Lie derivative which preserves some O1010 structure. And then I find up to this issue with the section condition, something that looks ODD invariant. When I solve the section condition, it gives me back a very particular theory of a metric, B field and dilaton, which is what I want in string theory. So that's quite nice. That's kind of the basic, all of the basic points that I want to make in this talk or in this example. So we're trying to describe geometry of theories with metrics and P-form fields. And the claim is that by shifting to a notion of generalized diffeomorphism, we can fix these actions in terms of field content, which knows something about symmetries like the T-duality symmetry. So I'll just put a little recap of what I've just said on the screen with the Kluser-Klein case and the double field theory case. So the main difference is this change from having in Kluser-Klein theory, the higher D theory had GL D+1 diffeomorphisms, and in double field theory, we've changed that to a notion of an ODD generalized diffeomorphism. So I'll just pause again for a few seconds in case any questions are lurking in people's minds. Okay. So what we've done, well, I very briefly talked about Kluser-Klein, where I had A in one form, double field theory. I'm dealing with B in two form. So obviously we can keep counting. And now we want to talk about what happens if I don't have a two form, but instead a three form. So we've been successful so far, so we're going to keep going. And okay, the logic is again, in general, string theory contains all manner of B forms, but in particular, 11-dimensional supergravity, as I think I mentioned, the bosonic field content of 11D supergravity is just a metric and a three form. So that three form couples electrically to the M2 brane in the same way that this B field couples electrically to the string. So now we want to try and do the same thing for that 11D field content. So I've slightly changed my notation when I talk about exceptional field theory. So, okay, now again, looking at a d-dimensional theory with a metric. Now I use ij as my d-dimensional indices, and I have a 3 form which transforms under both diffeomorphisms with vector v, and under 2 form Gates transformations with parameter lambda. And the claim is I can reproduce the same sort of structures that I described for you in the DFT case, where I extend my coordinates by introducing now dual coordinates that carry 2 indices, 2 anti-symmetric indices. That's the same structure as these Gates transformation parameters themselves. And I combine my vectors with my 2 forms to create some sort of generalized vector. And the claim is going to be, I can write down for you a generalized diffeomorphism which respects a different group, an exceptional group. And I can define generalized metrics which package this metric and 3 form together and reproduces their symmetries when I truncate away the dependence on these extra coordinates. And so first of all, we should ask, well, what is this sequence of groups? So here I've denoted it by ED bracket D. So this is a sequence of Lie groups that for 6, 7, and 8 corresponds to the exceptional Lie groups E6, E7, E8. And for lower values of D corresponds to some more mundane groups that you will know as matrix groups like SL5 and so on. If you like Dinkin diagrams, all of these groups form a sequence, whereas as I go to lower rank from larger to smaller D, I just cut off the leftmost node in the Dinkin diagram. The bracket notation here, ED bracket D, that's just telling me that I'm dealing with a particular non-compact form of the Lie group or Lie algebra. That's just like the difference between O2D and OD bracket, OD comma D. That's just a technicality. Normally in these slides, I'm writing ED, but here I'm being a little bit more precise. So these are also then, of course, the U-duality groups that you find if you reduce the 11-dimensional supergravity on a d-dimensional torus, although again, we're not basing what we're doing immediately on that fact. So, okay, the basic philosophy is the same, but okay, here I've got some dots because things get a bit more complicated now. So, okay, there are 2 complications. First of all, just putting a metric and a 3 form together does have a nice ED structure up to D equals 4. When you go beyond D equals 4, you have to include extra fields. The fundamental reason for this is that this ED symmetry relates the original degrees of freedom with their electromagnetically dual degrees of freedom. So for instance, this 3 form in 11 dimensions has a 4 form field strength. It has a 7 form dual field strength, which I can write as D of a dual 6 form Gates potential. And this ED symmetry actually relates components of this 3 form with components of the 6 form. So there's some complicated structure going on here where to actually get representations of ED, you have to put components of C3 together with components of C6. This is because it's the duality underlying this, the U-duality is a non-perturbative symmetry, which for instance relates M2 branes to M5 branes. And the M2s coupled to C3 and the M5s coupled to C6. So that makes things a bit more complicated, and the Gates symmetry structure is a little bit more complicated, but okay, it will be handled for us by the representation theory. The other complication is to do with the dimension of space-time. So for double field theory, we were kind of lucky in the end. I talked about it being ODD and D dimensions, but I could set D equals 10 at the end of the day, and I would get like, the full piece of the supergravity I wanted. Here, I would really like to go to 11, but if I go beyond 8, I end up with some infinite dimensional Lie algebras, which people have looked at for a long time from this point of view, and people have made quite a bit of progress in understanding how to deal with these, but it's a bit more complicated. Well, it's a lot more complicated. So just setting D equals 11, we're not really going to be able to do immediately. So we can actually pick any of these finite values of D, but then we're only describing some subset of the full 11-dimensional theory. So we also, as well as a generalized metric, we have to include some additional metric and Gates fields for the 11 minus d dimensional part of space-time. So that just says there's extra fields. It's not just a generalized metric and some scalar. It's a generalized metric and a whole bunch of things with indices. But that's not too bad. I will describe where these fields come from and what they do. So first of all, let me focus on the part that's like what we already said. So now I have something I will call exceptional generalized diffumorphisms. And I've written some formulae here which are useful, although they're quite vague. The problem is a lot of things you should do case by case, and the details depend on the group. But generically, we have these generalized vectors. All you need to know about them is that they're taken to transform in some specific representation of this exceptional group. I call this representation R1. I'll show a list of it. Well, I'll show a list of it now. And the general form of the generalized Lie derivative looks like the usual Lie derivative and some modification term. So this modification term involves something I call the Y tensor. It's just something built out of invariants of the Lie group in question. One way to define Lie groups is as the group of matrix transformations preserving some tensors. So for ODD, this YMN PQ was just the ODD's metric eta itself, eta MN, eta PQ. For a group like SL5, you get something a bit more complicated. So for instance, for SL5, this is the d equals 4 case. In this case, these generalized vectors live in the antisymmetric 10-dimensional representation of SL5. So to describe these, I need to introduce a bunch of indices. So I have a 5-dimensional fundamental index, and I write my generalized vectors in the antisymmetric representation as carrying a pair of antisymmetric indices. If I further decompose these in terms of some 4-dimensional indices, because this is the d equals 4 case, I get from the I5 component, I get a 4D vector. From the IJ component, I can dualize and get a 4D2 form. So that's how I combine the 4 components of a vector with the 6 components of a 2 form in d equals 4 to get a 10 of SL5. And in this case, this Y tensor is built using the group invariant of SL5. So SL5 preserves the Kronecker delta, and it preserves the alternating symbol with 5 indices. Because if I act on this with some SL5 transformations, I get back the determinant of the transformation, which is 1 times the tensor itself. So you could now go plug this expression in here, and you would find some explicit form for the generalized Lie derivative in that case. So you can sort of find that empirically, but there is also a nice group theory, representation theoretical way to view this generalized Lie derivative, which is that first of all, there's some derivative of the vector it's acting on that's always there. We call that the transport term. And then the second piece, which involves the Y tensor, can actually be found by requiring that what you really have is you take this derivative del of U, which is some GLN transformation, and you project that into the adjoint of your ED group. So you just have to look up what the form of the adjoint projector looks like for the group in question and the representation in question. And then this thing, for some choice of constant alpha, guarantees for you that you have a nice, well-defined generalized Lie derivative in which this second term implements an infinitesimal EDD transformation instead of an infinitesimal GLD transformation. Okay, so this has all been worked out. So there's a nice unified treatment of this in the literature. As before, you require that we have some notion of a generalized Lie bracket and some notion of a closed symmetry algebra. Again, there are obstructions because I've modified my usual Lie derivative. And my obstructions now involve contractions of derivatives, which again involve the usual coordinates and these extra sort of dual winding coordinates. These contracted with the Y tensor obstruct this closure, so I impose a section condition which looks like this. This has an immediate solution, which is to kill off these extra coordinates I introduced on the previous slide. Just note that's not the unique solution. There's a bit more freedom to solve this in different ways that will give me different theories. So I'll come back to that. Okay, and then once I've set up my basic notion of generalized Lie derivative, I can define things like the generalized metric, So now I can define in some way to be an element of ED itself, actually in some coset ED divided by some maximal complex subgroup playing the role of the Lorentz group. And depending on the dimension, I can write down parameterizations involving the metric and the free form C, which reproduce, when I solve this section condition, which reproduce the symmetries of the metric and the symmetries of the free form. I've got an exclamation mark here. I don't know if you can see it completely. I've got some funny factor of the determinant of the metric up front to make sure that this thing has determinant 1. And if you look in the literature, you'll see slightly more complicated formula sometimes because there's some issue with getting conformal weights out correctly, just as a side remark.
Chris, you have 10 minutes left.
Okay, thanks. Yeah, that should be fine. So that's how the internal, what I might call the internal sector works, the sector of the generalized metric. Now, I said that we can't do all of d equals 11 in an easy way, so we have to have some story where we have these extra extended coordinates, which are in some representation of ED, and we also want our fields to depend on the n-dimensional coordinates, where n is 11 minus d, which I haven't done any funny business with. They're just, in some sense, spectators to this extension that I'm doing. So suppose I have a generalized tensor which depends on all these coordinates. That's to say, I define its transformation under generalized Lie derivatives to be, sorry, its transformation under generalized diffumorphisms to be via the generalized Lie derivative. However, partial derivatives don't commute with the generalized Lie derivative. So if I take one of these n-dimensional partial derivatives of my tensor, it's no longer going to give me a generalized vector or a generalized tensor. But this is a standard problem, really. We know how to fix things like this. We introduce a gatefield, which will carry one form index like the partial derivative, and it will carry some index in the same R1 representation as generalized vectors and as these coordinates. And I define a covariant derivative, which means that this mathcal d of O is a generalized tensor, provided that A transforms in quite a natural way for a Gates field to transform. So what this A is, it's really like a Gates field for generalized diffeomorphisms themselves. This might seem a little unusual because we would normally view diffeomorphisms as coming with the Gates field in this way, but somehow this is because the formulation I'm describing is a hybrid between a gravity and a Gates theory. These generalized diffeomorphisms contain not only d-dimensional diffeomorphisms, but they contain Gates field transformations. So you get this slightly funny, but sort of halfway house object A, which is gauging generalized diffeomorphisms. And okay, given a Gates field, I try to define a field strength. I get some obvious expression involving this Lie bracket. It turns out that this thing isn't on its own going to be a tensor. You want the field strength to transform nicely under generalized diffeomorphisms. It fails to do so, and the way to fix it is quite interesting. It turns out you have to introduce an extra Gates field, which I've called B. And this Gates field lives in some other representation contained in the symmetric product of R1 with itself. And it appears in the field strength in this funny contraction involving the Y tensor and these derivatives with respect to these Ym coordinates. And it has to be assigned some transformational which guarantees that F is covariant, but then it also can be assigned its own Gates transformations under which the original Gates field transforms. And then, okay, given this, you construct a field strength for the 2 form. You find that it gives something that's nice, but you have to introduce a 3 form coming in under, again, some complicated derivative involving products of the Y tensor and partial derivatives. So what you get out of this is something it's called a tensor hierarchy. You get a sequence of Gates fields. So you get a 1 form in this R1 representation of ED. You get a 2 form in some other representation, a 3 form in some other representation, and you have some sort of nilpotent thing like an exterior derivative that goes from n forms to n minus 1 forms. So sort of in the opposite direction to what we're used to. And this thing squares to 0 using the section condition. So all of this kind of follows from this idea that I'm meant to be gauging generalized diffeomorphisms. So I just have an extra remark. I mean, the details of this have again been worked out. I just want you to take away that I kind of need to introduce a whole bunch of gatefields to get objects which are actually well-defined and tensorial. There's a nice conceptual way to look at this, which is to go back to the point of view that this ED transformation could be viewed as arising as the duality symmetry on reduction of 11D supergravity to n dimensions. And whereas in a normal Kaluza-Klein story, when I just had gravity, I could take the global GLD that would arise from a Kaluza-Klein reduction, I could gauge that, I could turn that back into the local GLD diffeomorphism. In exceptional field theory, what you're doing is you're trying to gauge the full ED symmetry in lower dimensions, and that's what's happening here. So I find this is a very useful way to think about it, but I have an extra slide in it, which you can see in the Google Drive folder, but perhaps I won't say any more about that now. So before I wrap up, I'll just briefly describe the action. So I've described for you that we have a generalized metric. We have some gatefields that talk to each other in some complicated way and have field strengths, which they all appear. And we also include, for this n-dimensional part of the space-time, some metric. And once we have the fields, we also declare how they transform into local symmetries. For instance, this ND metric is a scalar under generalized diffumorphisms. And I also have to specify how these fields transform under diffumorphisms acting in the external directions. Once I've done that, the action is uniquely fixed, all the coefficients, by requiring it be invariant under these local symmetries. So I briefly show you what the action looks like. You can fit it in one slide if you're willing to hide all the details. But basically, there's some sort of Ricci scalar for the external metric. There's things that look like field strength squared for the Gates fields. There's some internal part, which is like this generalized Ricci scalar in DFT, except here it also involves this n-dimensional metric. And for reasons to do with the dualizations that are going on, there's some complicated Chern-Simons or topological. Okay, and there are various technical details. You don't necessarily need to include all of the Gates fields because not all of them actually describe new degrees of freedom. Many of them are related to each other by various dualities. When n is even, you even have some self-duality constraints. This is only a pseudo action. But okay, the main thing to take away is once you understand the local symmetries, when you understand what are the fields you have and what representations they live in, this is fixed for you. It's fixed in the literature and described in detail in the review. And then you solve the section condition, and what you get back are the 11-dimensional theory I started talking about, or you can solve the section condition in inequivalent ways, and you can get 10-dimensional theories. You can get the 10-dimensional type 2b supergravity out of this as well. So this is a very nice unified formulation that captures on the same footing these different 10D theories, as well as the 11-dimensional supergravity. It's a little bit of work to show exactly how this matches, because you have to do some splitting of the coordinates in the 11 or 10D theories, and then do some field redefinitions to match to this. But it all works out very nicely in the end. So this is now my final slide. I think I have 2 to 3 minutes. So what have we actually achieved? I've been trying to describe to you something that you could call duality invariant supergravity, which is this doubled or exceptional field theory formulation in which you have both global and local ODD or ED symmetries. So all of my fields are in these generalized metric or generalized Gates fields. I have these generalized diffeomorphisms, and I've even introduced these coordinates and representations of ODD or ED. But of course, I have the section condition, and when I solve the section condition, that breaks the global ODD or ED, and it breaks the local as well. So if I impose the section condition constraint that I only depend on some D of these coordinates, this theory then reduces back to what is equivalent to 11 or 10-dimensional supergravity, possibly written in some funny split of the coordinates. On the other hand, because this has got global ODD or ED baked into it, if I would then combine this by actually truncating the dependence in all of the coordinates to Kaluza-Klein reduction of this whole thing, what I get is the same thing I would get if I started with supergravity and reduced to n dimensions. So this sort of automatically contains the information that you would find if you started here and did Kaluza-Klein reduction and some complicated predefinitions at this point. So that's kind of nice conceptually. It sort of says, well, maybe here's a higher dimensional perspective on how to get these duality symmetries. I should maybe always rewrite my supergravity in this d of t or x of t way first. And one advantage is that it's agnostic about whether I'm describing the 11D theory or the type 2B theory in 10D. That's kind of useful. But another way that it's useful is that you've kind of written the supergravity in a way that's adapted for dimensional reduction. And that turns out to be very powerful, not just for boring toroidal reductions, but for much more complicated things. So you might have some reduction involving some spheres with flux and God knows what, that perhaps produces a nice simple, let's say, some deformed or gauge supergravity in lower dimensions, where maybe some subgroup of the global duality group has been promoted to a local symmetry with some structure constants for its Lie algebra F. And even if the formulae for how this works in the usual approach to supergravity is very complicated, there's a wide class of solutions for which it's very, very simple in double or exceptional field theory. For instance, you have this notion of a generalized Shirk-Schwarz twist or reduction in which you factorize out your dependence on these coordinates y in this particularly nice way, where these so-called twist matrices obey nice algebraic conditions with respect to the generalized Lie. And this is not only very powerful for studying solutions of supergravity, but it also allows you to relax or weaken the section condition that I described. So you could put all of the information about it, really having dependence on the dual coordinates in these sort of twists and factorize it out of all your fields. And you can check that you can do this in a way that's consistent with having this closed symmetry algebra, but it's not as strong as saying I can never have any appearance of these dual coordinates. And this already gives you 10D theories in this way, such as the massive 2A or the generalized 2B theory, which might be known to people from the integrability side. So I just need to list a couple more applications and then I'm done. So this is kind of a step, letting these dual coordinates actually play a role is kind of a step about trying to go beyond supergravity. Another way to go beyond supergravity is to describe so-called non-geometric backgrounds in d of t or x of t. Something like this generalized notion of geometry here should be a natural home for things like t-folds or u-folds where you're meant to patch somehow by duality transformations. You'll hear more about such backgrounds in the next two talks of today. Another way in which you can go beyond supergravity, which I think is attracted a lot of interest and is very interesting, is that you can use the way in which these ODD or ED symmetries constrain the form of d of t or x of t to think about constraining corrections to supergravity, such as alpha prime corrections, in particular in d of t, or also people have worked out string loop corrections in maximal supergravity and x of t. And in addition, I think that this formulation has become now a useful tool also in directions that weren't originally conceived of when people were thinking about this originally. So I've mentioned a couple of other things here that I find interesting. This is a nice setup in which to study generalized notion of dualities like Poisson-Lie T duality and extensions to the U-duality case. That maybe doesn't seem so surprising, but the way in which it appears is perhaps not obvious at first glance. And then more unexpectedly, there are links to things like the double copy, where you describe gravity in terms of Yang-Mills squared, could be very nicely embedded in DFT. Because there's some sort of double copy generalized Lorentz group appearing. And you can even have stranger things like non-relativistic limits of supergravity because I keep describing these parameterizations of the generalized metric in terms of a metric and a B field, etc. But you can do stranger things where you don't actually have a well-defined metric, but you have a well-defined generalized metric and describe seemingly singular configurations in string theory, which is interesting. So I think there are also many more applications, either known or which will come and which I haven't thought of yet. This generalized duality story is perhaps one that's closest related to the integrability that people were focused on yesterday. So I don't really have anything more to say about that. So I will thank you for listening, and I hope that you've now got some idea about what these theories are and what they do.
Thanks very much, Chris, for the